The Big Bang Theory has long provided a framework for understanding the explosive genesis from which all known matter, energy, space, and time have emerged. Yet, a question lingers in the shadows of our cosmic understanding, challenging the very foundation of our cosmic narrative. Was there a universe before our own? While a range of empirical evidence supports the notion that the universe has been expanding and cooling for the last 14 billion years, the idea that it began with a bang is pure speculation. It is based on extrapolating back in time, assuming equations remain valid under conditions far beyond where they have been tested. So, the Big Bang Theory itself does not provide specific details about what preceded the singularity, or whether anything existed before it. To answer the question of whether anything existed before our universe, we need to delve into a realm beyond the reach of traditional telescopes and into the speculative yet fascinating territory where physics, philosophy, and cosmology intertwine. As we peer back through the cosmic timeline, approaching the singularity from which our universe is thought to have sprung, we encounter a frontier that defies the laws of physics as we know them. Here, in the very fabric of the early universe, scientists seek clues not in the stars, but in the mathematical and theoretical underpinnings that suggest our Big Bang might not have been the beginning after all. This exploration becomes even more critical in light of the observation that the universe is expanding faster and faster, a phenomenon that continues to perplex the scientific community.
So there are ideas for the answer to that question. We have astronomical observations that we need to be sure are compatible with the predictions of our theories and so forth. So we as good scientists do what needs to be done to try to test these ideas. But the idea that I think most physicists or cosmologists buy into at the moment is that gravity can have two manifestations. The usual form of gravity that you and I know about is the attractive version. You drop something toward the Earth and it moves downward because the Earth and the object pull on each other. That's the ordinary gravity that we experience every day of our lives. But Einstein's equations actually allow gravity to also be repulsive. It can push outward as opposed to just pulling inward. And this is something that we have never experienced because the gravity created by a rocky object like the Earth is always the attractive variety. The gravity created by the Sun, again, a compact object, is always the attractive variety. But Einstein's math shows that if you don't have a rocky object that's isolated in space, but rather energy that is uniformly spread through a region of space, that kind of entity yields repulsive gravity. If the very early universe, if it was filled with a uniform bath of this energy, we call it the inflaton field, the name doesn't matter, but if it was filled with that energy, it would have been subject to repulsive gravity. What does repulsive gravity do? Pushes everything apart, causes everything to rush outward. So the bang of the Big Bang may have been a spark of repulsive gravity operating with a tiny region of space that pushed everything apart.
Not all scientists agree on what is causing this acceleration, which only adds to the intrigue surrounding our cosmic origins. Several hypotheses and theoretical models have been proposed to explore what could have existed before the Big Bang. Proponents of the cyclic model believe that our universe didn't just emerge out of nothing. These models suggest that the universe undergoes an infinite series of expansions and contractions known as Big Bangs and Big Crunches. According to this view, our current expanding universe will eventually collapse back into a singularity, only to explode again in a new Big Bang in a never-ending cycle. Albert Einstein considered the possibility of a cyclic model for the universe as an everlasting alternative to the model of an expanding universe. However, these early attempts failed because of the cyclic problem. According to the second law of thermodynamics, entropy can only increase.
So the idea of a cyclic universe had been around. When we discovered that the universe is expanding, that was on the list of possibilities, that the universe could then begin contracting and bounce, and that this would get rid of the problem of having a beginning of time if it were cyclical forever into the past. And that intrigued people. Maybe we're spending a lot of time trying to explain something, the Big Bang, which never happened. Maybe there's another logical possibility to be explored, and ultimately you want to turn that into a theory. The idea of bouncing in those days was that you would bounce until all of space-time disappeared, and then reappeared, and then expanded and contracted and disappeared again. So it was this kind of bouncing universe, and it led to this kind of problem that if you think about the disorder in the universe, whatever disorder you had in one cycle would be recontracted or reconcentrated as the universe approached the bounce, came to zero size, and would be there when the universe began the next bounce, but it would influence through its gravity that next bounce. So instead of that next bounce being identical to the one before, it now has whatever disorder it's going to produce plus the sum of all the disorders of all earlier cycles. And then that meant that the cycles couldn't be identical, the amount of disorder that would distinguish one cycle to the other. And the cycles, in fact, must be growing in duration, going forward in time. So you didn't get rid of the beginning. You got back to the beginning. And so that discouraged people from thinking about cyclic models for a number of decades.
According to Paul Steinhardt, a series of recent advances strongly suggest that the only way to describe the remarkable homogeneity and isotropy observed on large scales may be if the universe first underwent a period of ultra-slow contraction. This leads to a new novel cyclic theory of the universe in which the Hubble parameter, energy density, and temperature oscillate periodically, but the scale factor grows by an exponential factor from one cycle to the next. In recent studies documented across 2 research papers, scientists have critically examined various models of the bouncing universe concept. Their findings cast doubt on the idea of a cyclically renewing universe, suggesting instead that the universe we observe might be a singular occurrence, not part of an ongoing cycle of creation and destruction. According to Stephen Hawking, the state of the universe after the Big Bang will not depend on anything that may have happened before, because the deterministic laws that govern the universe will break down in the Big Bang. Hawking proposed a model in which the universe has no boundaries in time. Instead of a singularity, the early universe would have undergone a phase of rapid expansion driven by quantum effects. According to this model, the universe has no origin as we would understand it. Before the Big Bang, which happened about 13.8 billion years ago, the universe was a singularity in both space and time. Hawking suggested that if we could travel backwards in time towards the beginning of the universe, we would note that, quite near what might have been the beginning, time gives way to space so that there is only space and no time. So as Hawking himself explained, asking what happened before the Big Bang is meaningless because time as we understand it did not exist before the expansion. Advocates of multiverse theories propose the idea that our universe is just one of countless others in a vast multiverse. They suggest that beyond our cosmic horizon, there could be an infinite number of universes, each with its own laws of physics, histories, and configurations. According to these theories, what we perceive as our universe might merely be a small part of a much larger ensemble of universes, some of which could be vastly different from our own, while others might be strikingly similar. This concept opens up possibilities for explaining certain cosmic mysteries by suggesting that different universes in the multiverse can have different properties. For instance, it might help understand why the physical constants in our universe are finely tuned for life, proposing that we simply live in one of the many universes where conditions just happen to be right for life as we know it. A new theoretical study offers a tantalizing glimpse into the cosmos's continual evolution. According to recent findings, our universe might not be expanding in isolation, but could be merging with nascent baby universes, contributing to its ongoing expansion. This notion not only challenges our understanding of cosmic growth, but also suggests a complex, interconnected cosmic web, where universes give birth to, interact with, and absorb one another in a perpetual cycle of creation and expansion. This revolutionary idea, emerging from the depths of theoretical physics, hints at a cosmos far more dynamic and interconnected than previously imagined. It suggests that the fabric of our own universe may be stitched together with threads from other cosmic realms, each contributing to the tapestry of space and time we observe today.